This is okay. Now let me talk about double cusp of first species. What is double cusp of first species? Let me talk about double cusp of second species. Double cusp. Sorry, this is single cusp. I'm sorry. First, let me take single cusp of second species. Single cusp of second species. What is this? Single cusp of second species. There is a tangent, and these two curves are lying in the same direction of the tangent. So these two curves are, this is first curve, second curve. They are lying in one direction or in one direction of the tangent. So this tangent, these two curves are lying on one side of the tangent. These two curves are lying on opposite side of the tangent. Okay, so this is single cusp of second species. Single cusp. This is one cusp here, and second species, because these two curves are lying on one side of the tangent. So, okay, this is what we call single cusp of second species. These are two basic different kind of cusp. Single cusp of first kind, single cusp of second species. This is single cusp of first species. This is the other two basically. Now double cusp of first species, double cusp of. So this is the third one. Let me talk about. This is the fourth one. Now what is the double cusp of first species? I'll talk about this. First species or first species. Now then double cusp of second species. Double cusp of second species. Okay, just double of this. I'll talk about. And double of this. If this is single cusp of first species, what? If I define it, then we say that if there is a normal and the two curves are lying in one side of the normal, Okay, the two curves are lying opposite to the tangent, undoubtedly, but they are lying on one side of the tangent, one side of the normal. If I draw a normal here, this is normal, means making 90-degree angle. This is a normal. In one side of the normal, if the two curves are lying, that is known as first single cusp of first species. Single cusp here of first species. First species is that when two curves are lying on opposite sides of a tangent. This is first species. Second species is when two curves are lying on one side of the tangent. Second species. Okay, if there is a normal here and the two curves are lying on one side of the normal, that is also single cusp of second species. Single cusp of second species here. Okay, now double cusp of second species. This. If I take that there is a tangent here, and this is the point, and these two curves, this is a single curve here. Okay, and another curve is this. Let me take this curve here. I'm sorry. This is a point here, double point. At this double point, these two curves are lying in two sides. If there is a normal here, this is normal upon this tangent line. Okay, so these two curves are lying in both sides of the normal. And this is a double cusp of second species. This double of this. If I draw a tangent here, normal here, and the same kind of two curves, if I take to this side also, it's two curves, and this is second cusp. This is second cusp. Double cusp of second species. Single cusp is single cusp of second species. This is double cusp of second species. Try to understand. Okay, so this is double cusp of second species. Now in this case, if I take this kind of this is tangent line here. Now one curve is lying in one direction, okay, and the curve is lying in opposite of this. This is just double cusp here. This is double point here, but these two cusps are in opposite direction of a normal. So in both sides of the normal, there are first single cusp of first species. If they are repeated, this is double cusp of first species. Double cusp of first species. This is double cusp of first species. Just double of this. This is double of this. Double of this. Okay. Now what is the okay? Then another kind, there may be a inflection, that may be inflection type of point. And let me talk about another kind, fifth kind of cusp. What is the fifth kind of cusp, which is known as mixture of the two kind of cusp here. Okay, for the two species, if are combined together, two species are combined together. Let me draw that figure. And what is this known as? I'll talk about. Okay, so if there is a tangent here, suppose this is the tangent. Okay, and if there is a double species, this is double cusp of first species. Okay, double cusp of first species, and if there is another curve, okay, and this is here like this. What does it mean? It means this is the first species, single cusp of first species type, and this single species of second. These two are combined together. This is a mixture of both these species. This is a mixture of or conjunction of combination of, let me take combination, and this is known as point of inflection here. Combination of two species. Combination of two species, first and second. Why? At this point, this is the second kind of species. Second kind of cusp. Second kind of cusp. There is a beak type of this, and this is the tangent line. This tangent is here. Now this is the first species, first kind of cusp, which is known as just like a node type. This is a node here, or this node, and this is the cusp. But this is not node; it's a cusp here. Node is something else. Okay. Now in this case, these two cusps are of the two varieties type. First species. This is the first species. This is second species. These two are combined together. This is a combination of two species, first and second. This is the second one. This is the first one. Okay. These two are combined together. This curve is this intersecting at this tangent line. So tangent, if the tangent of a curve intersects it, okay, then it's known as point of inflection. I'll talk about when with the point of inflection. I talk about second type, multiple points, and then point of inflection. So this is point of inflection, which is known as, I'll just talk about it. So first variety, cusp of first variety, I've talked about first species, second species, and then single cusp and double cusp I've talked about, the single cusp and double cusp. Now, if I talk about, then what is this is known as point of, okay, this point, let me talk about P. The proper definition of this point is also known as point of Oscul-inflexion. Oscul, O-S-C-U-L, inflection. This point is known as Oscul-inflection. Oscul-inflection. This point is known as, okay, this point is known as point of Oscul-inflection. Point of Oscul, O-S-C-U-L, inflection. Point of Oscul-inflection. This point is when there is a mixture of both the first species and second species of cusps. This is second species cusp of single cusp. This is for first species of single cusp here. Okay, single cusp of the two kinds, the two species are combined, this is point of inflection known as Oscul-inflexion point. Okay, this is next variety. Now let me talk about what are the other points. I mean, the first two kinds of species are also known as what kind of cusp? Okay, the first cusp and second cusp, what are they are known as? Okay, now first is keratoid cusp. The cusp of first species. The cusp of first species or first species. The cusp of the first species is also known as keratoid cusp. Is also known as keratoid cusp. What is keratoid cusp? Keratod means horn type. Horn. This is okay. Cusp of first species, which was horn type. These two horns are there. Okay, this is the tangent point here. Keratoid cusp. Keratoid. This is keratoid cusp. Keratoid cusp, or in other words, horn-like cusp. Horn-like cusp. Okay, so this is horn-like cusp. Two horns are there. Okay, this is horn-like or keratoid cusp, known as keratoid cusp. Keratoid cusp or horn-like cusp. Okay, that is horn-like cusp. Okay, so this is horn-like cusp. And what was the second type? This is beak of a bird. The second cusp. This is keratoid cusp. The first species, this one. This is first species. Cusp of first. Single cusp. This is single cusp of first species. Or first species, which is also known as keratoid cusp. Okay, what is the second cusp? Second cusp of second species, which is also known as, let me talk about. Now, the cusp of second species or second species, single cusp or double, maybe both. I mean, let me take this one. This is beak-like. This is known as beak of a bird. Beak of a bird, but its proper name is also known as, let me talk about that also. This is first species, sorry, the cusp of second species. Single cusp, this is single cusp of second species. Okay, which is beak-like of a bird. Okay, or beak of a bird type. And is also known as RAMPHOID cusp. This is also known as RAMPHOID cusp. Okay, so let me talk about what is a RAMPHOID cusp. This is also known as beak of a bird type, or beak-like RAMPHOID cusp, or beak-like cusp. Beak means beak of a bird. Okay, so beak of a bird that we know about. So this is a beak of a bird. Okay, with double one, that is double cusp. This is single cusp of second species. We write here second species. We can write also second species. Different kind of species there. This is RAMPHOID cusp. Important one. RAMPHOID, keratoid cusp, and Oscul-inflexion. Okay, because there was a mixture of both the single cusp and second cusp. Sorry, this first species cusp, second species cusp. When they are combined together, okay, then that's known as Oscul-inflexion. And this is RAMPHOID cusp, beak-like cusp. Keratoid cusp is horn-like cusp. Okay, so these are basically types of cusp we have talked about. Now let me find out that how to find out the double points of it. Okay, tangents at the double points. Basically, how to find out the double points, whether they are double points or not, or tangents to a double point. How to find out tangents to a double point? Let me talk about how to find okay, tangents to a double point. Tangent to a double point or at the origin. To a double point or at the origin. How do we find out this? Okay, so the basic important point is that whatever, suppose there is a linear equation is given, okay, or any rational equation is given, okay, any rational equation, if it is given, algebraic equation or any linear or quadratic equation is given, then that out of that equation, okay, we have to equate the lowest degree or the lowest degree term to 0 or term or terms. That is how we find out the tangent to a curve. With the double points, how to find tangents to a double points or at the origin. So just simple point. We have to equate the lowest degree term or terms to 0 to find out the tangents at the origin. Find out the tangents at the origin or at the given points. What is the necessary condition at the given points? Now, what is the necessary condition of at the double point of tangents to be there? Okay, so what is the necessary condition at the double points to find out the tangents? What is the necessary condition to find out the tangents at the double points? What is the necessary condition? Let me talk about. First of all, the lowest degree, because tangents are 2, there are 2 tangents here. So to find out the 2 tangents, at least second degree term must be there. That must be equal to 0. Only then we can find out double points, because double points are there. To find out double points of an equation, it must be quadratic equation at least. Okay, so double degree must be 2 degrees, second degree function of term must be equal to 0. Okay, it is the requirement of a function here. For example, this is second degree, y square equal to 0. So the lowest degree term of this equation we have to equate to 0 to find the tangents at the origin and double points of the curve. So double points we have to find out at the origin, tangents have to find out. So the condition, necessary condition, let me find out. Necessary condition to find out the tangents at the double point of a curve. At the double points of the curve. The necessary condition. Let me talk about this. The necessary condition to find out the tangents at the double points of a curve. At the curve, if there are 2 points there, or at the origin, you have to find out the tangents. So what is the necessary condition for that? If the equation of a function is given, let me take. If the equation of a tangent of a curve, equation of a curve is given, let it is fxy equal to 0. This is the equation of a curve. Let me take this as the first one. Okay, now if I differentiate it by partial fraction, differentiating it by partial fractions, which is the function of action by both, by partial fractions, partial differentiation, not by partial, but partial differentiation. Differentiating by partial differentiation. Partial differentiation means in parts. So let me differentiate it partially. What is partially differentiation or partial differentiation? Let me define this. So this is, take this as f. Okay, fx by means f. The first condition is f must be 0 to find out at least two tangents. And what is the condition? Let me differentiate it with respect to y, with respect to x, sorry. Differentiated partial fraction with respect to x. So we get, if there is a function given, okay, of a curve like this, then we have to differentiate it with respect to x. So we will get del f del x plus, now because it's a function of y also, so let me, we are differentiating with respect to x, but we have to write it as del f upon del y. Okay, this is d by dx. What does it mean? We are differentiating with respect to x, but it is the function of y also. So second function, it will be d by dx. So del y and dy, this we have added. This is del f upon del x, no problem. This is the second equation here. Okay, to find out the tangent, to find the tangent, to this curve. Okay, d by upon dx equal to 0. We have to substitute. But here, we have to find out two tangents. We have to find out here. We have to find out. This is the second equation here. We have to find out two tangents. But okay, we have to find out two tangents. Here only one dy upon dx equal to 0. One tangent is denoted by this. One tangent is obtained from this. Tangent is obtained. Only one tangent is obtained from this equation dy by dx equal to 0. So to get the double tangent or two tangents, what the condition for that? Let me further differentiate it. Okay, further differentiation. The second equation was del f upon del x. This was fx y equal to 0. This was the first equation. The second was del f plus del x and del f del y. This is dy dx. This is second equation here. Okay, so just to obtain double tangents, so to obtain two tangents from second equation, the required condition is del f upon del x must be 0, del f del y must be 0, and f equal to 0. Means this function must be equal to 0. The three conditions here. Then we can find out two tangents. Now what are that there are 2 points here, double points. What the condition for that? If I differentiate this equation further with respect to x, so just to find out the condition of having two double points here, or tangents are distinct or real or something. For that, let me differentiate this equation with respect to x. So further differentiating second with respect to x. With respect to x, so we get, let me differentiate ddx of del f del x plus ddx of del f del y d by dx. Let me differentiate this. What is the differentiation of this? Let me change it. Okay, so differentiating it now further, and then we have to find out quadratic equation, and this quadratic equation will give something. Okay, and from that we can find out that what is the condition for the two tangents are real, okay, distinct, coincident or imaginary. Okay, so that we will talk about. What are the conditions for that? Let me talk about that. Ddx of this function, first one, will be del square f upon del x square, first one, plus, just to be differentiated in that way, it is nothing but del square f upon del x del y. The second condition. What we have done here, so this is first, this is f here, del square f upon this ddx of this, del square f upon del x square, first condition, but it's a function of, f is a function of y also, so again del square f upon del y del x. So this del y, with respect to y, we have to differentiate it. This is this one. Now plus, let me differentiate this by multiplication, rule of multiplication. This is first, second. Okay, then let me first differentiate with respect to the first term here, del f upon del y, it will be del square f upon del x del y, first step, into, sorry, this, what I've done here. So dy dx is also here. This is dy dx as it is. Now in this case, because we have taken here this del x, I'm sorry, this dy dx is also here. Why? This is del square f upon, because we have to differentiate with respect to y also, so y multiply, so dy upon dx is here, this dx is here, and this del x del y is again. So let me, I'm sorry, this second step of this was, I didn't complete it. Let me write here, del square f upon del x del y, and this is dy upon dx of this function, differentiating this with respect to y also. So del y dy upon dx here. Now this function of first one, dy dx as it is, differentiation of this with respect to x, this del square f upon del x del y plus this function. Okay. Now second, this is plus sign here, first time. Now second step, differentiating this with respect to y here. So this del square y upon del x square. First is del f del y as it is. Differentiation of this with respect to x here, it will be, okay, this will be dy upon dx whole square. Del square y upon del x square, del square y upon del x dx square. Okay, so this is the second step. Then plus sign, there is third step also. Again, if I differentiate it with respect to, okay, y, this will be dy upon dx whole square, because dx, dy we have to multiply. So this will be del square f upon del y square, this one, del by we have to multiply, so it will be dy upon dx whole square. Okay, so this is differentiated in three terms, this and this one. Now try to understand. This is first one, we have differentiated with respect to x, undoubtedly this first function, second as it is, so this is first function del square f upon del x del y, this one, dy dx as it is. Third step, Now this is to be differentiated, del f del y as it is. Now d by dx, and this is d dx. Differentiating this second time, it will be del square y upon del x square. Okay, then but this function completely, we have to take this with respect to y. Okay, this is a function of y as well. F is a function of y. Again, f is differentiated with respect to y. D by dx, one more will come as we differentiated del f del y. That is del square f on del x del y. So del y square, we multiply by del y here. Del y upon del x, this del y and this del x will command this. So this d by dx will again come. That will be square of this. Now these terms, so this del f on del y from first position, that it is 0. Now since, let me write here, del f upon del y equal to 0 from second equation, that if there are two tangents, then del f on del y equal to 0, del f on del x equal to 0, and f equal to 0. That was the condition we put there. This is 0. This step is 0. This equal to 0 here. This is step. So now these two are similar terms. Let me write them again. Let me write them here. So what is this equation? Let me first write this equation. This term, I mean del square f upon del y square into dy upon dx whole square plus 2 times this middle term. This is del square f upon del x del y into dy dx plus what is independent term? Which one? Sorry, this one. Del square f, the first step, upon del x square equal to 0. Okay, so this equation equal to 0. So this whole equal to 0 here. So this was 0 here. So second equation, this was differentiated with respect to x. We have obtained these terms 1, 2, 3, 4, and 5 terms. Out of this 5 terms, this term is cancelled out with 0. But del f on del is 0. This is 0 here. These two are added up. So this are written down first. Sorry, this one first one. Del square f on del y square in d by dx whole square. Plus these two are added up. Twice of del square f on del x del y. Okay, this del x del y and d by dx. This one d by dx. So this equation is now quadratic in d by dx. What is this equation?